Hey everybody! Right, let's see if we can solve this problem. First of all, this is my first attempt at doing a video similar to this. I've got a really crap tripod set up over the kitchen counter and using the phone, and basically if this doesn't work, well, tough. Okay, question I want to answer is, does frequency, mains frequency, have an effect on a video game when you convert power from US power, or Japanese, to UK? What I want to do is I just want to talk about a tiny bit of theory. I'm not going to get into mathematics and things like that. What I'm going to try and do is cover some of the topics. Now, this is the second take of this video. I've already tried to go through it once and draw it out, and unfortunately, for whatever reason, the camera decided to not record. So let's try again. All right. So point number one: UK power is between 220 and 240 volts at 50 hertz. USA power and other places out in the world is 110. Japan, I think, uses 100, and a lot of the rest of Europe uses like sort of 220. But the USA uses 60 hertz. So this is a rough look at what that looks like on an oscilloscope. Two things laid over the top of it. So we've got a first line here, which is UK, which will be quite a wide pulse. It's the one that goes all the way to the end. UK. I don't have multiple coloured pens. And the other one is US. There's more pulses basically per second is what we're getting at. So the distance between here and here is shorter. So this is 1/60th of a second. Right? Well, measured in hertz, 60 hertz. So that's basically the difference on the oscilloscope between US voltage and UK voltage. Does this affect video games? Right. Okay. Short answer for all the can't be bothered to watch to the end is no, it doesn't. And here's why. For the rest of us who are actually interested in learning something and expecting life to be handed to us on a plate. Let me see if I've got the slides the right way around first. I'm not exactly going to win an A for preparedness today. Yes, looks like I have. Yay! Okay. So first of all, we have in a normal cabinet, what we have is input from the mains here. It goes through a fuse, it goes through a transformer, and a number of other things in the circuit, and creates 110 volts, roughly 120 volts for the monitor. In the case of, say, a Pac-Man game, some AC voltages, and then a marquee tube are usually about the same, whatever the main line voltage is, it's the same on the input. Now, the reason we have to do conversion is two things. First of all, the monitor won't work at 110 volts. And secondly, the tube will blow up at 110 volts. Even though this is part of the way through here is creating isolation between that side and that side. But this transformer here is literally just, it's dumb. Transformers are dumb. And let me give you an example of what I mean by that. Transformers are dumb. So here's your typical transformer. And we'll say it's got a ratio of 2:1. If I put in here 220 volts and give it exactly 220 volts, I'll get exactly 110 volts back out the other side, give or take 1 volt. Or give or take a small amount. But I will get from 220 approximately 110. If on the same transformer I was to put 440 volts in at 2:1, I'd get 220 back out. So going back to this one, the problem here is that this setup here is designed for 110 in and creating 110 or 120, so a step up or a step down for all the other voltages. If we just put standard 240 volt mains straight into here, we will get whatever the ratio is on the other side. So if it's 1:1, we'll get 220 volts here. These will all go up, so you'll have 14 volts and 20 odd volts going to the board. That's no good for it. And we'll have 220 going to the marquee tube, and the ballast, the electronics for that probably just will not take it. You probably see it go very, very bright and then just stop working again. So that's why. So we insert, usually in our case, we put a nice chunky toroidal, which is designed to keep down hum and also keep heat down as well. And we insert it literally just before the start of their power chain inside the cabinet. So we take 240 from our mains here in the UK, pass it through our toroidal. On the other side we get 110. We feed that into the cabinet main wiring wherever it would normally start. So effectively putting it just before the plug. Now, why do we do this process? Why do we actually mount them inside and not just go and buy a converter from Maplin. Well, it looks ugly. It's an extra thing you've got to carry around with you. It's another set of very long wires, usually floating around at the back of the cabinet. Right, so that's why we do that. So moving on, voltages. When we get inside a regular, sort of a normal sort of game, we've got our transformer to 240 volts, 2 to 1 step down, 110 volts, some other magic in the middle, and a switch mode power supply or some kind of power supply board, and we'll get our 5, 12 and -5 DC. Now what's DC? So DC is direct current, AC is alternating current. That's what AC looks like, up, down, up, down, up, down. Goes through a bridge rectifier somewhere in the power supply and some other circuitry and becomes a positive voltage or a negative voltage depending on how it's configured. But all it is just a flat line like that. There's no swing in it like over here. So that's DC. DC has no frequency. It's just direct current. It's just going that way. It's not alternating. AC is alternating, goes up and it goes down. This is just staying constant and going in one direction only, forwards, whereas that has a positive voltage half the time and a negative voltage the other half of the time. Okay? Now then, how does this not affect video games, is the question here. So the reason it doesn't affect video games is because of the way the clock circuitry works on the board. And that's what this will explain to you. 5 volts going into the board, which is the normal way it's done, goes into the PCB and it supplies power to an oscillator. That's the crystal, or the X-tel as it's referred to in a number of times. In an example here we're going to use, I originally used 18 megahertz when I drew this out the first time. We'll just say it's whatever, it's n megahertz. But basically, even though you've got a DC voltage coming in, what we have here is a pulse that's coming out at a specific frequency. But we have DC in, no frequency involved in DC, and we get a frequency out because that's what this is generating. It just needs 5 volts to power it or similar. But it makes its own frequency. Notice that's not 60 hertz or whatever, that the main frequency is a lot higher. Doesn't get changed because we've gone to DC. There is no alternation going on. There is no frequency of pulses. It's just one voltage. So this thing's going pulse, 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 pulse at 18 megahertz. 18 megahertz via some other stuff gets into what we call the clock circuit. And the clock circuit then generates pulses. We have a TV up here. Here's the top left. Everything's at 0. That's the end of a line, and that's the end of the screen. As the pulses happen through usually through a couple of counter devices, and there's far better explanations than what I can give you about this. You get different pulses. 1H is for the dot moving along the screen. There will be 15,076 of them per horizontal line. 1H, 2H, they're just referred to these as pixels, as counters. If you binary map these, they become decimal numbers, 1, 2, 3 if you put 2 and 1 together, and so on and so on and so on. You can actually figure out exactly where you're on the screen and capture that gun with some other electronics, and you could do a screen split horizontally if you really wanted to, things like that. Every time we hit the end of a line, so these count up and ripple and ripple and ripple and ripple and ripple until we get to the very end here and we get this end pulse. So at the end of our screen, it pulses, which moves another set of counters, which is the vertical counters, down a line. 1, 2, 4, 8, blah, 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 all the way down until it gets to the bottom of the screen. For every end of the line, you get an H blank pulse, and for every end of the screen, you get a V blank pulse. But these are at frequencies that are derived from the crystal oscillator, not the mains. So what does that kind of look like? Well, that's what your H blank and V blank signals end up looking like. 15 kilohertz and 1/60th of a second. A 256V, which is basically when it's done, it's carried basically past all the counts that it can do, which, don't forget, going back to here, it doesn't just go one like that, like an LED moving up a screen. No, it will go 1, and then that'll go off, that'll come on, then that'll come on with them together. So 1, 2, 3 to get 3, 4. Although 4 and 1's 5, 5 and 2 is 6, 5, 2 and 1 is 7, and so on and so forth. 4, 2 and 1 is 7. And so it'll keep lighting these up until it gets all of them lit up, which would equal 255. And then it will count one more and get usually an extra pulse. I've only drawn it to 128 and 128 because I drew it out wrong. But ultimately, all those pulses basically mean positions on the screen. We get to the very, very bottom of the screen, we've had 60 of those. The bottom one, the very, very last one down the screen, happens once every 60th of a second, because that's just the way that timing with the others moving down and the clock and everything causes it to happen. So that's how we get 60 hertz. Basically, in a nutshell, there is no DC frequency to worry about. We get 60 hertz out of the board because the oscillator crystal that's on the board divided by n number of times equals 60th for every V blank pulse. So how does that affect monitors? Well, again, it doesn't, and here's why. So you've got our voltage going in from the line, 110 volts, and the first thing that the monitor does is makes DC for its own power supply, because it has low voltage and it has medium voltage and high voltage. So we end up with about 120 DC. And again, originally we had an AC voltage going in, and now we have a DC flat line. Then there's some other electronics through a transistor, some kind of little drive transformer makes pulses. So basically something will switch this transistor here, which is usually called the either you've got your pre-drive transistor or the horizontal output transistor, but anyway, it will drive through this circuit, it will drive the flyback. The flyback is just getting pulses. The whole point with induction, to create an actual waveform going through here, is it doesn't have to go to the full negative of the voltage, it just has to drop. Now, the lower the drop, even with, effectively this is what would be half wave rectification, somewhere into the terms of half wave, it will still be enough because you've got high voltage followed by a low voltage. And those are enough to create that magnetic field through the transformer, the high voltage transformer, which then creates you however many kilovolts your monitor tube needs. So it could be 18 kilovolts, 22 kilovolts, 27 even for bigger screens. But the point here is that, again, the power goes in, goes through a circuit, becomes DC, and then DC then uses its own methods of creating pulses at its own speed that it needs. This was all well designed originally. So very, very well thought out. And thought through in those terms to basically make it that as long as you had the correct power going in, you wouldn't need to worry about frequency because the system makes it. Now modern day systems are really crap and decide to muck you about immensely. The only other thing to cover here is the marquee. So the only thing here is we've got 240, goes in through our transformer, goes into the cabinet wiring and comes to the marquee. Just one or two of the marquees that we've looked at do actually say 60 hertz only and won't work. If we put them on a frequency corrector, we do actually get them to work. The only thing we can do there is basically just change the ballast out. There's no point in trying to embed a frequency generator into the thing. It just adds way more. It's cheaper to just swap the ballast for a 50-60 one, because most of them, all the Atari ones seem to be, most of the Namco ones seem to be, they all say 50/60 hertz, but they are rated only to 110. So it's not like you can just put 240 volts into them, they won't work. The tubes are only rated for 110, but will work at 50 or 60 hertz. And that's it. So the takeaway here from this is when a cabinet gets AC, no matter what frequency it's getting it creates the right voltage through our transformer and then makes DC. Of its own accord, DC has no frequency, therefore frequency doesn't matter. That's it. In a nutshell, that's it. Hope you enjoyed this brief, quite hurried and probably in some ways a little bit technically inaccurate or shall we say less detailed way than it could be. I don't have time to go through all the theory of operation and everything. There's plenty of reading you can do on the internet for that. Anybody who wants to have a stab at doing a better version of this, please feel free. I apologise if you can see, to me I can see a huge kind of shadow off the tripod here. I'll get a better setup for doing another one of these at some other point. But hope that kind of solved all the questions about that which were raised on the other video that I did about doing a power conversion on a Kangaroo machine. Alright, so till the next video, give us a like if you liked it, give us a thumbs down if you didn't. That tells us something. We'll ignore all the ones that do give us a thumb down. And please do, if you haven't done already, please do subscribe so that you can get notified when we do more videos. Plenty more coming soon. Have a great day and we'll see you on the next video.